Hey there, I'm Arianna. Today, I'm going to talk about our work on modeling human visual search performance on realistic web pages using analytical and deep learning methods. This work was done when I was an intern at Google Research in collaboration with Yuan at Google Research. Modeling human visual search has been a long-standing challenge in HCI. Traditional approaches require UI researchers to conduct time-consuming usability tests with real human users. If we could have a computational model that can predict search time, it will dramatically save the time and cost of UI researchers by offering them some insights into search difficulty before they test real human users. Actually, a lot of classic results have been established in the field. For instance, people have found that the number of distractors would influence search time, and so does the prior knowledge of the target. Several HCI researchers have proposed computational models to simulate visual search time. However, there are two major limitations in previous research. The first is that previous models usually use a limited set of structured features, like target location, sizes, shapes, and colors of the target, and so on. But that means previous models cannot go beyond those limited structured features. In reality, there are many unstructured features that are hard to articulate, yet important for prediction. Secondly, previous models usually make strong assumptions about the tasks or human behaviors, but they may not always hold. For instance, the Cogtool Explorer assumes that links are organized in groups and humans search hierarchically, but this is not always the case. What we really want is a model that can take an arbitrary realistic web page like this, and a target like this, and predict how long it will take the user to find the target. Ideally, this model should not only work for image stimuli, but also text stimuli. Given a super busy web page here, and a text stimulus like this, the model should be able to predict how long it will take the user to find the target. To answer this question, we turn deep learning for help. Deep learning has been quite successful in transforming many fields these years, including object detection, natural language processing, and even multiplayer competitive games that have challenged humans for thousands of years. Deep learning has gained increasing attention in HCI recently. For example, Yuan and colleagues have used deep learning approaches to model vertical menu selection. In the current work, we want to take a more ambitious step. We want to build a neural network model that can predict human visual search time on realistic web pages. But we don't want to throw away all the previous findings on how structured features can predict search time. Instead, we want our model to flexibly integrate both structured and unstructured features. And finally, we don't want our model to be just a black box. We want to have some understanding of the model behavior. So, how do we do that? Here's our model architecture. We have a convolutional neural network that processes the raw pixel of the image, and we have another convolutional neural network that processes the raw pixels of the target. Each of them will extract the representation of the image and the target. The representations are then combined to compute an attention map. This attention map indicates where the model should attend to in the image, and it is further used to compute a representation of the unstructured features in the picture, image, and the target. As I mentioned earlier, we also want our model to integrate structured features. In our model, we have a fully connected layer that takes the concatenation of the structured features, including target location, number of objects on the web page, and also target size. And this fully connected layer will give us a representation of structured features. The representation of the unstructured features and the representation of the structured features are then combined to calculate a final representation, which will then be used to predict a scalar, the search time. Next, let's look at how the model is trained. To train our model, we use a dataset collected by Google via crowdsourcing. The user was shown a web page like this, which was randomly selected from the internet, and also a target, which was randomly selected from the web page. And the user needs to find and click on the target. Their search time was recorded. The dataset contains a total number of about 28,000 trials, and they were performed by about 1,900 human workers. Let's first look at some analytical examination of the data. Here we plot the normalized search time against various structured features. We see that as the y-coordinates of the target position increases, search time also increases, meaning that when a target is further down on the web page, it takes longer to find. But it doesn't really depend on the x-coordinates of the target. These results indicate a strong vertical search strategy. We also see here that as the target size increases, the search time also becomes shorter, meaning that the bigger the target is, the easier it is to find it. We can also plot the search time against the target type, and we notice that the images are the easiest to find, and the text is the hardest to find. Now let's move on to model performance. To quantify how well our model is doing, we calculated the correlation between the model prediction and the ground truth data, and we report the R-squared. For within user R-squared, we calculate the R-squared for each user, and then we average them. For cross-user R-squared, we just mixed all the trials from all users and calculated a single R-squared. For the models, we first build a couple of linear models that take individual structured features. And we can see how these individual structured features predict the search time. We also have a linear model that takes all the structured features and predicts the search time. And finally comes our deep learning model that combines unstructured features and all the structured features. We can see that our model outperforms all the models that use only structured features. For cross-user R-squared, the conclusion still holds. We also asked our model to perform a classification task in which it needs to classify the search task into one of the 5 categories: super easy, easy, neutral, hard, and super hard. And we can see the chance level is 20%. Our model outperforms all the models that use only structured features. We also use our model to perform a binary ranking task in which the model needs to decide which of 2 search tasks is easier. The chance is 50%, and our model outperforms all the models that use only structured features. Although our model is so far the best model, as I promised you guys earlier, we still want to have some understanding on how the model performs the tasks. To get some intuition on the model prediction, we look at the attention maps learned by the model. And we found that the model learned sensible attention maps. For instance, in this case, the model is asked to predict the search time of finding a target like this. And we see that in the attention map, the model learned to highlight all the images and ignore the text. In other trials, where the target is a text stimulus, and the model learned to highlight all the text and ignore the images. We believe the sensible attention maps really help the model to predict user search time. To summarize, we propose a unified framework to model realistic search tasks, such as arbitrary web pages in the internet. It can flexibly integrate both structured and unstructured features, and it demonstrates the great potential of deep learning in HCI research. For future work, we plan to further boost our model performance. You may notice that there is still a lot of room for improvement in terms of model performance. And also, in the current work, the model is only able to predict the search time, but in future work, we want the model to be able to give some concrete suggestions for better UI designs so that the search can be easier. That's all I have today. Thank you for your attention. If you have any questions or comments, feel free to contact us.